Okay, good morning, everybody. I see we've got a few viewers online already who've come bright and early to get started, so thank you for joining me as we kick off what's now going to be the third stream that I've done here, building PyO3, Rust and Python together. I hope you're ready to get involved and give me some comments if you've got any ideas on what we're building, questions if you've got any to ask. Yeah, I'm looking forward to doing some more of this today. Good to see you again, Peter. Thanks for joining. Um, so I was just going to say, this week I have tried to look at the chat latency. I think last week we had accidentally got it on like a low or a normal or slow latency setting by mistake. So I think there was quite a long delay between chat messages being sent and when I could see them, and maybe also between when I was speaking and when you can see me. So I think I've tried a lower latency setting today. I think it means that the quality of the video connection might be impacted a little bit. So if it seems like a problem, let me know. Otherwise, hopefully it means that we can get a slightly faster communication line between the two of us. So that'd be great. I was just going to look and introduce what we're going to talk about today. So 2 weeks ago, if you'll remember, we looked at, let me bring up the Edge window browser. We were looking at class methods in the Rust API. So we're sort of stepping away. Last week we looked at the C FFI, mixing C code and Rust code. This time we're looking a bit more at the procedural macros again. So really focusing on the Rust code. We're talking about supporting Python class methods, and in particular PyO3's new API, this bound smart pointer, and we wanted to allow references to this thing to be passed into class method. I actually, since the stream 2 weeks ago, I've lost the sample code that I was writing, but let's just draft that out again quickly. So for a bit of a refresher, here we have some PyO3 code that you might write as a user. We've got an empty Python function here, and we've got a Python module, and this is written as Rust code, defining how to build, a Python function that does nothing and a Python module that contains that function. But we were looking at classes, so let's add a class again. That class doesn't need to contain anything for now, but we can give it some class method. And we got to a point where so the first argument is class, and we now have this bound smart pointer working for class method after the stream we did 2 weeks ago. And so that's this PR that I'm showing up on the left-hand side. And I promised at the end of that stream that I'd go finish that PR off, tidy it up, tests and documentation, get that all complete and merged. Naturally, I had other pieces that I was working on since, such as the FFI stuff that we looked at last week. So I haven't actually gotten any further with this PR since we looked at it 2 weeks ago. So I thought it'd be a good story to continue to look at this one together. And there's actually some more functionality that we can add to this PR as well. So I think it'd be cool to do that and refine it on stream today. Hey, John. Hey, Amarudin as well. Thanks both for joining too. Okay, so just as a sort of reminder of what we did in a bit more detail, we had in the existing PyO3 API, we can have this kind of functionality where instead of taking this smart pointer containing a Python type, we took a reference to a Python type expressed like this instead. And this is the API that we're calling I call it the GIL-refs API, but ultimately we're going to remove support for this in PyO3. So one thing that would be cool to do, if we can manage to figure it out on stream today, is make it so that we get a deprecation warning if you do this particular expression in your code, because that would help obviously users migrate to the new form that we want them to be using. And then the third form that we supported that already is supported by PyO3, but we looked into, is where we have this Py smart pointer instead. And this one we're going to continue to support. The goal for future PyO3 APIs is to have this form with the bound Py type and this form with the Py type instead. And we're getting rid of this one. So this is the old one. getting rid of, and this is the new one that we're just introducing. And so where we can go with this, we've got the tests to tidy up, we've got documentation to touch, and we'll look at those maybe in a bit. But before that, let's look at other cases which are very, very similar to this, where we can refactor what we did 2 weeks ago to make it support some additional cases. And actually, we've got one of those 2 cases I was thinking about right here at the bottom of this code. So here's our Python module definition, and you can see it's a function. This is the name of the Python module. The first argument it takes is this Python token. It carries a lifetime to tell us that we can safely interact with the Python interpreter for the length of this Rust lifetime. And then we've got this second argument, which is a reference to a Py module. And the sharp-eyed amongst you will notice that this is exactly the same form as we have for what we're calling the old deprecated API and this class method form. So we'd like to be able to tell people that they can also do the same thing with Py module. I think if we tried a second form of this, that we don't actually support the Py smart. Oh, maybe we do. I don't remember looking into this particular piece of the code for a long time. Oh, here we are. Now we're getting some compile errors now that I've hit save. Yeah, this compile error is looking like what I'm expecting. You can see that it's telling us that it wanted a function pointer that was taking this reference to a Py module, and we've instead given it one that's got the smart pointer. So absolutely, this form Py smart pointer of Py module isn't currently working in PyO3 0.20. And it's not too much of a problem because this one works, and that's more than good enough. It might be nice to support this form for symmetry, but what we really want to do is make sure that at least this form works, which I'm pretty sure we're also going to get the same compile error. Yeah. We also have a compile error here just because we haven't imported PyType. So let's do that. Okay. And okay, and then it looks like we're going to have a second interesting case inside this wrap.py function macro. So this one is a little bit more involved. I think we might come back to this after I introduce the other case, which is more similar to class method. So I think it will be easier for us to solve that one first and then generalize, hopefully, the solution that we'll have built for the 2 to come back to solving it for the Py module as well. I just realized that for some reason, oh, here we are. I couldn't see the chat. Okay, so the third form is like, if we just go back to the code that works for the moment. Sorry, this is just me feeling like I need to solve the compile errors, or warnings in that case. The third form is to do with Python functions. So it's possible, it's a feature of the Python C API, to have the function, which is called, know what module it was associated with. And so PyO3 exposes this by this pass module option. And then what we expect is to take one additional argument, which is that module. And let's try and explain what that means in a little bit more detail. So let's just print mout. And we'll compile this code. So we've updated my function to take the module it was associated with. And then here we can see down here in the Python module, we're adding the function to the module. So we should be able to go back to our terminal and compile this. Here we are. I've increased the font size on everything a little bit this week again as well. So if the font's looking too crowded, let me know. Hopefully for mobile viewers, it'll be a little bit easier to read this week. I think it was just a little bit small for mobile views when I was looking at this myself. So we'll see what it looks like. I think in the terminal, it's now quite crowded, but hopefully it's still workable. If not, then we can play around with different ways to lay out stuff maybe next week. Okay, so we'll go over to this Scratch code base and we'll run matcher in to compile this code. Oh, I haven't activated a virtual environment yet. Okay, here we go. So now if we run Python, we can import our function that we've just defined. And why is it not printed anything? That seems a little bit unexpected. I've used print instead of print line. So I suspect it's probably buffering. And if we run this a bunch of times, we might eventually get something. Let's see. Yes, but that's not a very nice output. So let's change this to print line. And then when it prints, it will both add a new line and flush, which is probably more what we want. So let's do that again. So now if we run the function just once, the point I was going to try and make is that we're printing the representation of the module that got passed in, and well, we can see it's given us what looks like a Python wrapper, so that's as we expect, and it's particularly telling us, well, it's this PyO3 Scratch module. For reasons I won't go into right now, it's actually, this is like the package, and then the Rust code gets compiled into a submodule, but we import from the top level package directly. And we also get the, this is the file path. So you can see where it lives on my file system, and in particular that it's in a .so native compiled library. I'm running Python 3.11 at the moment. Maybe I should be thinking about updating this to 3.12. Wait, maybe we'll look at that later. I don't think it makes a huge difference really, but there we go. Certainly 3.12 is nice for the performance wins and other new features, but I just haven't got around to updating this particular virtual environment. Okay, yeah. So, and then just to show, I guess we could, if we want to show the same thing directly from Python, then I talked about it being a submodule, so we'd have to look at this thing, and we should get the same wrapper as we got above. So this is just the module object referred to directly in Python, and here we've passed it using PyO3's framework into your Python function or that you've defined. So this could be useful, I guess, in particular cases where you want to store other data on the module and you want to be able to load stuff from it. And so we want to have this form work instead, right? We want to get it to work for the new API. So we want to support this bound PyModule type. And sure enough, we're getting a compile error now. Let's see what that looks like. Maybe it might look nicer in the terminal on the left. Oh, slightly so. It's a bit cramped, isn't it? That's okay. So anyway, it's pointing out that here, the trait from reference to PyModule is not implemented for reference to bound PyModule. So if you watched the stream 2 weeks ago, you'll see that that's pretty similar. It's the same kind of problem where before we were converting from, we had a from conversion that was just allowing these two forms to work. And then we implemented some code to allow the conversion to the bound type to work as well. And so maybe let's just switch back to the browser for a second and have a look at that diff that we pushed as a bit of a refresher, and then we can go digging around from there. Oh yeah, here we are. So there was a little bit we had to change in the procedural macro code. So it's still using that into conversion or from, as we just saw in the compile error. But instead of creating or calling this function from type pointer to create that reference to PyType, we introduced this bound type wrapper, which then had this other function pointer to bound, also in the, both of these being inside PyO3's implementation details. One for So this one was a wrapper that implemented these from conversions, and then this function, we got that. That's just a test change. Yeah, so we had bound type, which had all these from implementations attached, and then we had pointer to bound, which just took some Python object pointer, a reference to it, just so that we could tie the lifetime in a safe way. We had quite a big discussion on the first stream about getting that lifetime right. I don't really want to repeat all that, but the point is that this function allowed us to quite, in a safe way, express that we have a Python object, of which at the moment we don't know the type, but we did in our procedural macro code a downcast. We didn't actually check because we were trusting the Python interpreter would always hand us a type object for a class method. And then, so yeah, we had any Python object and we had it safely for some lifetime A, which we could just use for basically the duration of the class method. So it's here's the reference again. We don't have A written here, but we could write it like this instead if we wanted, just to make it look more similar. In fact, there's this Pi lifetime as well that the bound pointer is saying we can safely interact with Python references for. And so, yeah, here's the same type, but instead we converted it to a Pi type through this downcast it unchecked in the macro code. And so I think what we'll do is we'll go try and pull apart these things that we wrote 2 weeks ago and get it to instead support this new situation for the PyFunction parse module. And so we're going to have to make some of this code a bit more generic, and we'll also go figure out where in the procedural macro code this parse module stuff came from. So maybe we'll start there. One moment. So having just done a quick search for parse module, then what we're looking for, I guess, is somewhere in the PyO3 macros code. So what do we see? We see this link. This is defining that keyword. This looks like, let's go look at this code in a bit more detail. So this is just recording when we wrote this option into the Python function, that we actually, it's recording the different possibilities that we have. So we have parse module, we can allow setting the name of the function or the signature. Those are all documented on PyO3. Let's not talk about those right now. Instead, let's have a look. This is still, oh, it's a bit big, isn't it? Can you folks see the font okay while I've got the find window open, or is this a bit too hard to read now? Maybe we'll think about making it one size smaller again, or we could make the VS Code window bigger. Let me know in chat if any adjustments you think might be helpful. Otherwise, what I'll try and do is hide the find window so that we can read things very briefly while we're just looking for the right piece of code. But if you can't see anything at all, then that's not great. So that's all still to do with storing these attributes, I think. So this is probably, oh no, that doesn't quite look right. What's going on here? Oh yeah, so this is restricting parse module to only work on probably Python functions. I suspect that what we'd find is that we could probably try and put this here and we'll get that error message. Yeah, parse module cannot be used on Python methods, which is what we saw over here. So that's explaining what that is. So we must be looking, not there. So it must have been, it must be in that other file. Oh, here we are. This looks like it. So if we've set parse module, then we set the method type. Hey there, Pontus, thanks for joining. We set the method type So this is deep inside PyO3's proc macro code. Let's talk about this fun type enum just very quickly to give you a sense of it. There are lots of different types of function we can write with PyO3. I mean, we've looked at class method, PyFunction here. You can have a new for a class. So that's defining the Python constructor. And then we talk about a class method. You can combine new and class method, static methods, and then it looks like how this pass module is implemented is we set it to this special fun module type instead. Because we saw that here, that if the pass module is set, then we are changing the function type to be a module function. Otherwise, we're calling it, as far as PyO3's implementation is concerned, a static method. I mean, I guess that's kind of right. A static method doesn't take a class or self or anything as a first argument. So a freestanding function in a module kind of works in the same way. But yeah, so we're looking at this fun module. So that's leading us a little bit towards where we're heading. I guess let's look for that instead then. Okay, there's fewer hits. What have we got? This is in the signature generation, so that's unlikely to be what we're looking for. This looks like it, and it's right next to where we were working last week, actually, or 2 weeks ago, isn't it? So here, this is the code we were looking at 2 weeks ago, where we had this into conversion, and we used this bound type. We were just talking about all this in the browser. And then here's the fun module hit just beneath. And so at the moment, we're just using some of the old PyO3 APIs to get the reference to a Py module here. So I think we can do the same kind of trick, right? We have this pointer to bound we know was taking only it produced any Python object. So I think at least we can do that, and that will give us let's go back to it. That's where we're looking. So it's going to give us this reference to any bound, and then we're going to need to convert its type to PyModule. And again, the code that was there before, this isn't doing any type checking. I know that just because of experience of using the old PyO3 API. So I think we can get away with, for the moment at least, let's do the same pattern of not type checking. So we can do a downcast unchecked again. Great. And so now we're getting a reference to, it was just underscore SLF. So we'll write it like that and see what happens. And then this, I guess we want to match it. Let's match both in the same way. I think the difference here without the cast, for watching the stream on from 2 weeks ago, this came up because in one particular case where this class method was being called, the pointer that was being given in was actually a pointer to a PyType object rather than the Py object. So we had to cast it to the right type. Whereas I think here we just probably can get away without the cast. So we'll leave it like that. And let's see what we have over in our Scratch code now. So now this new function's working, but the old one's not, which is what we found before. And so we're going to have to do the same kind of thing again. We wrapped it in this bound type for the class methods. Maybe let's go for the same kind of idea. Why not for now? Maybe we'll tidy this up into something more uniform for everybody, but we'll start with that. And then maybe we can make this generic in a moment. We'll see what goes on. So, okay. Yeah, no, nothing works. That's because it doesn't exist at all. So let's just copy paste this first. And then everywhere that we see type, let's just call it module. And I guess we're going to have to import it. And so as a reminder, this is just a wrapper taking on that bound PyModule, and then we're giving it 3 from implementations to get out to the target types we want to support. So the reference to PyModule for the old API, the new API's bound PyModule, and then also we can have the PyModule supported as well. And so now I think this code compiles. Let's see. I'll switch back to a terminal. Compiling. Oh, it's warning us that it's never used. Yeah, that would be a good idea. Let's change this to also call second function. So we're now adding both of these to our PyModule. We can compile again. And we should find now. So this is the existing one, still works. And now we've got the second one that we just made support, and that works in exactly the same way, which is what we want. So that looks great. Okay, so shall we try and make this generic now for the 2 types? We could go that way, or we could try and solve the PyModule case here. Oh, that's also PyModule, so that's quite interesting. So that means that actually the 2 sets of implementations we've got now, the PyType and PyModule, are good enough, because this is also PyModule that we want here for this 3rd case with PyModule. So we could try. So let's just solve this first, and then we'll come back and look at the making the whole thing generic maybe, or tidying it up a little bit in a moment. So to figure that out, maybe let's go back to what we did 2 weeks ago and do cargo expand, because I think that's quite a nice way to have a look at the source code and figure out a bit what's going on. Because unlike with this past module one, where it was in the end very, very similar to what we did before, I think I'm almost certain that this PyModule expansion is going to work quite differently. So as a reminder, we've got this. No, that's not what I'm looking for. Yeah, this great command line tool, cargo expand, that will take, well, whatever source code you want to target for. I'm telling it to compile the library, which is just this single line of Rust or file of Rust source code here. And then we'll emit the expanded form to some other file. And the expanded form is where all of these macros have basically gone, ingested all of their Rust source code and spat out the transformed Rust source code, so that we see kind of the next step on what the Rust compiler is looking at. And so let's run that and see what we get. I guess side by side might be a bit tricky with this font size. Let's see what people think if I do that. Maybe we can look at it in this scale just for a moment, just to get a sense of where we are. And then I think we'll probably bring it back into a single file just so that it's easier to read. So we've expanded this file on the left. What are we looking for? We're looking for these imports line up like this. This is stuff that the Rust compiler's added in the top to do with the standard library being available and the standard traits like from and into. We've then expanded this function here. It looks like, oh yeah, so this is the expansion of what the PyFunction macro turns into, where again, this is the original function that we wrote. The print line macro has been expanded. And then we've got all of the stuff that PyO3 adds underneath. This is quite a fun trick, actually. So we've defined a function. You can actually have a module named the same as a function in your same source code, and these both get imported in the same place. So PyO3 uses this for a bit of macro trickery down below to do with the wrap PyFunction macro. So let's just jump through all of this. We've got function 2 here. We can keep going through that. Here's our class. and this must be the generated Py class output again. We've got our implementation of the class with all of those macro annotations removed. Here's the output of all of those macro annotations, lots of it. And here we are, here's the PyO3 scratch function. So this is what we're looking at here. And so here's our procedural, or our expanded result of the PyModule macro. So let's just look at that in a bit more full screen size. So we had, as a reminder, this wrap PyFunction macro, which was being used as part of adding the functions into the module. And then we've expanded those into this form from inside PyO3. It's basically just calling a helper function again. So we won't worry about that right now, but I think we're going to have to come back to that. And then underneath, this is the result of expanding that PyModule procedural macro into the code which is setting up the Python module. And so we've got, there's a lot of details going on here. What can we look at? So we've created a module again. So we've done the same trick where we had a function and we've created a module with the same name. That's useful for being able to import these things from one file to another. So it's quite a nice technique. I can show that maybe in a little bit more detail. What I mean by that is that if we wanted to have some like sub module, or this could be another file, then we can actually use PyO3 Scratch like this. And this will be both referring to the function that we've got here and this hidden module. And so depending on how you're using this in macros, well, we could have, I guess, another PyModule. Yeah, maybe it's a good way to show it. Then because we've created these two symbols, one as a function, one as a module, it's part of the machinery of how this like wrap PyFunction macro actually manages to work, because this import super my function is pulling in both the function definition and this hidden module, which has got some extra stuff defined inside it that PyO3 can use to do what it needs to do. So it's quite a neat trick, but maybe that's a bit of detail for another time, really. So what have we got? We've got, we were down here in the procedural macro for the module, and in particular, we were trying to work out how this PyModule reference is getting passed in. And so where do we see this PyO3 Scratch symbol being used? So we called the module. Here's the symbol being creating the name of the module in the Python side. This is the symbol that we're exposing from the native library for the FFI, so that when the Python is importing this module, it looks for the symbol of this name and will run this code. So this is where we're kind of aiming to look. Particularly, we're looking at this def static, creating a new module. And I think here we have this static is of type, it's a PyO3 internal type module def. And we're going to have to click around, I think, to figure this out. It looks like this function is getting called to create this type. That sounds right in my memory. Let's go look at what this type is. So we're looking in impl PyModule.rs. So we're looking for this makeDef type in PyModule.rs. I mean, makeDef, that's not creating any matches. No, sorry, module def. Okay, so the module def is an implementation detail of PyO3, and it's the pieces that we use to build up that Python module's definition, so that when importing, you get the desired result. Basically, it's telling PyO3, well, it's the information PyO3 needs to build up that Python module so that the import statement works as you want. So let's look through. We've got this. So the first, we're talking about, it's a wrapper around an FFI type. So we can actually see that here. So this is the C API's definition of how to create a Python module. So we've got base. We might maybe need to bring up the C API documentation to refresh my memory on this one. This is getting a little bit more involved than I thought it was going to. Does that look readable on screen? Oh, I need to bring up the browser. Here we are. So if we create, do we get a hit here? Yeah. So this is a definition of the module def. So that will help us remember what's going on here. Okay, so the base is just something that the C API doesn't really talk about, other than saying that we need to set that to a particular value, so it's fine. The name is obviously the name for the module, so that's what we're going to store as this PyO3 scratch symbol here. That's fine. The documentation, so PyO3 can set the documentation. We can actually do it. If we put a Rust doc string above, then this gets turned into Python module doc string as well. We didn't put that in our expanded module, so we don't actually see that here. So we can't see that right now, but that's fine. It's probably like this was the documentation here, if I had to guess. We could see new, yeah, the doc is the second argument. So this empty string just with a null character is all that we passed for a documentation, because we didn't put anything here before. The size, okay, so then this talks about module state and module methods, and more detail. I actually think that as far as PyO3 goes, we don't use any of those other fields yet. So I don't really think it's worth us diving into those in more detail. So let's go back to what we're doing with the module def. So we're creating a Python one, and then we've got what we're calling a module initializer, which is what we use to create the module, if I recall correctly. And it looks like this is correct. This is taking a Py module here. So this is going to probably be the piece of code that we're going to have to change to support PyO3's new API. And then after that, we've got, so Python 3.12 has these sub interpreters. My module def is a Py object. Oh, okay, thanks, Peter. So PyModule def is just allocated like any other Python object then, I guess. So that's why we need to have the base. That makes sense. Okay. So yeah, Python 3.12 has these sub-interpreters, so that you can have multiple interpreters running in tandem. And the point of this is you can do this for isolation reasons, for sandboxing, or you can also do it for parallelism. You can get a per interpreter global interpreter lock. And PyO3 doesn't support this yet. It would be really cool to make it support it, but it's a sort of like, I guess, a research piece to figure out how that all comes together soundly in a Rust expressed way. So at the moment, PyO3 just disables that. And we've kind of got like two steps to that. One, we try and remember the actual interpreter where the module was first initialized, so that we don't allow the module to be initialized again with another interpreter. So we only ever allow you to do one interpreter, no sub-interpreters. And then we also actually cache this thing in, if we saw, this is a static symbol, this module def. So it's written into the program memory in a fixed location. And so we can save this. And then if you ever tried to import the module again, I think you'll always get the same one, which we do as a kind of deliberate safety valve. I guess it's not strictly necessary. I think this was a recent addition to PyO3 a couple of versions ago. But the point is that it means that if you're importing the same module again, then you're going to get predictable results. And if you try and import in a sub-interpreter, you're not allowed to. So this is kind of like a limitation of PyO3 at the moment, but it's a deliberate one for correctness reasons. And maybe in the future, we'll figure out how to express that sub-interpreter behavior correctly so that we won't need to have that restriction. So let's just take a quick look back at our procedural macro code. We have, this is the entry point where when we're importing the module, we can see what's going on. We're going to call this function, which calls through into PyO3's internal code to do a module limit, and it's calling this def.make module. I don't want to talk about the trampolines. I think I might have mentioned them and the context of how they protect against panics and things like that 2 weeks ago. So let's just skip over that detail for now and instead look at this make module function. So that's on this module def that we've created, in particular PyO3's wrapper around the CAPI's module def. And so that function is here. And what have we got? So it's taking itself, it's actually requiring itself to be in static storage. I guess that's probably just a sort of making sure that we're really doing what we intend when we're caching these things. And then it's taking this Py argument to prove that we've got the global interpreter lock held. So it's allowing us to do things safely while we've got that marker there. Okay, we've got a bit of code that's statically, or it's conditionally compiled only for PyPy before PyPy versions of 3.8. So this is for actually quite old versions of PyPy now. We've got a protection for, it looks like PyPy versions older than 7.3.8 are known to have a compatibility issue which may cause crashes. Okay, that's undesirable. So I think if I remember when we put this in, PyPy had changed their program ABI a little bit in a way that was prone to crashing. And so the best thing we could do in PyO3 was just warn and be like, hey, be careful, use newer versions of PyPy. So we've got that there. Okay, this is check that the interpreter ID has not changed. This was what we were talking about preventing sub-interpreters. PyPy doesn't have them yet, so we don't even need to do this on PyPy. Let's just jump over that sub-interpreter code, but it's basically checking that the ID matches what we expect. We can raise an error if it's not. And then finally, we've got this bit where we call the module we've wrapped inside what we call a GIL want cell, or global interpreter lock want cell. This might be an interesting thing to talk about very briefly. So in the Rust standard library now, we actually, in the Rust standard library, this is now called OnceLock, I think. Yeah. Oh, have I still got the browser up? Yes, good. So OnceLock is a Rust standard library type. And the idea with OnceLock is that you can write to it exactly once. And you do that normally in some lazy fashion, in some later moment than at program startup. So when you first need the value inside it or something like that. And then because you can write to it only once, if you ever get the reference to data from inside of that, then because it's write once, you can guarantee that that data is not going to change. So in Rust's notion of references, you can get as many shared references, this _t, to this thing as you like, because, and this is an option because it may not be initialized. But there's another function, getor, in it, which is what we have very similarly written in for PyO3's GIL want cell, where if it's not initialized, it will run the underlying function f to initialize the value, and then it will either return the newly initialized thing or it will return what was previously there. And so in this fashion, you can call this function as many times as you like. You're only going to have the OnceLock be written to once, and if you and then you can freely read this thing as long as you have a reference to the OnceLock after that. And so the difference on PyO3 side is to do with the synchronization. So OnceLock, I think, works by blocking or it's an error to reentrantly initialize. Yeah, current implementation deadlocks. And so if you're trying to do this from inside PyO3, what you often end up doing is you start hitting pieces of Python code which can cause you to block on the global interpreter lock. And if you're doing that, then because this can deadlock and the global interpreter lock is also a lock that can deadlock, you can easily introduce deadlocks into your program. And so the reason that PyO3 introduced this Jill once cell type, or I guess if we were to update to newer terminology, we might one day call this Jill once lock, but I guess for historical reasons, we added this before the Rust standard library did. This OnceLock used to be in a third-party ecosystem crate called OnceCell, and that's where PyO3 got the name from. But the difference in Jill OnceCell is that we use the global interpreter lock for synchronization. So for our getOrInit function, unlike OnceLock, which just takes a reference to self and the function to initialize, the Jill OnceCell's getOrInit also takes proof that we hold the Python global interpreter lock. And that way, we're guaranteeing, again, still, that there's not going to be any synchronization issue when we're writing into this thing. But we're not going to have deadlocks related to the Python global interpreter lock because we know that we've got the Python global interpreter lock here and we can have predictable results. So, I mean, the astute amongst you might be aware of Python 3.13 bringing what it's calling free-threaded Python, where we're going to be doing away with the global interpreter lock as a blocking thing to do thread synchronization with. And so this Jill OnceCell type is absolutely one of the things that PyO3 is going to have to rethink in the very near future to be able to support Python 3.13. But we've got that here today. We're still only supporting up to Python 3.12. So as far as we're working on code today, we will just continue to use this Jill OnceCell. And then maybe a month or two down the line, I think we're going to start looking at Python 3.13 support here on these streams. And so probably one of the things that we're going to have to think about is what on earth we do with this Jill OnceCell type and how we could expand it to support a world where we don't have the global interpreter lock as a blocking mechanism. And probably using the standard libraries OnceLock might be quite a nice way to do it. But we'll have to think about the edge cases, like PyO3 will be trying to support both Jill Python and free-threaded Python for some time yet. And so we'll have to talk about conditional compilation and what does it look like to get a consistent API between those two things. I think there's quite a few questions to answer at the time. Anyway, that was a little bit of a digression. Let's talk again about what's going on here. So we've got our cached module in a Jill OnceCell. And when we're calling get or try in it, we're trying to create one of these new modules. We use it. This is PyO3's way to create an owned Py type from a raw FFI pointer. We're doing an FFI call PyModule create. And so that's with our FFI def. So we already looked over at the C API's PyModule def, and we said that PyO3 is using some of those first few fields. And so we're creating that module as an object. And then we are going from that module. We're then calling self.initializer. And self.initializer was this module initializer. It's a wrapper around, this is a function pointer here. It's a function that takes a Python token and a Python module object as a reference. This is the deprecated API that we're trying to move away from. And it's going to return a Rust result PyResult particularly is just a type alias for this form instead. Basically, it's a result that contains either no value on success or it contains a reference to a Python error. We've written it as this PyResult because this pattern happens a lot in PyO3, so it's nice to have a type def for that. Okay, so this is going to get quite a bit more thorny, I think, because this is all written in the type system here as it takes this reference to a Py module, and that's not in macro code per se. This is now inside PyO3's internals, where all the macro code did is state that this symbol PyO3 scratch, which took those two pairs of arguments, does indeed behave in the way that we thought, and then forwarded that initializer on into the module def. So somehow we're going to have to change the procedural macro code to give us a bit of flexibility. But I'd like to keep, it's nice to keep things where possible into nice typed Rust inside of these implementation submodules of PyO3, because it's much easier to reason about code that's written in these normal modules rather than what expands out of the procedural macros. So if we can, I'd like to try and get just as much into the macro code as possible to make that work, and then leave the rest to be inside this submodule here. So what am I thinking? I'm thinking, well, first we know that we're going to need to change the type of module initializer, because there's absolutely no point it taking a reference to the deprecated type anymore, because we want to change the PyO3 API off that. So at the very least, let's start by changing this to look like this instead. Oh yeah, we'll need to import this type. And we're going to have a few compile errors pop up as a result of that. So let's just think about those. So this is fine. We can change this. Hi David, thanks for joining. Great to hear that the font size is good. Okay, so now previously we had asref, which is converting a Py into the old API, and I think bind is the right correction here instead. What have we got here? These are in test code. This is in test code. Oh, this is just because we've changed the type here, so we need to actually just import. In this new bound API, this is looking at the Py module type now. When we have a reference to Py module, then all of these functions that we were calling, like add function, were defined directly on the Py module type. And so they were just freely available. But for the bound smart pointer, what we end up needing to do to get that to compile in the same way is we have to introduce a trait which has the same functions available, add function, and then we implement that trait for that smart pointer, the bound Py module. And that's kind of a bit of a, dare I say, it's like a complexity that's introduced because of limitations of current Rust. I don't think we need to talk about that too much. The issue where I talk about the bound API on PyO3's GitHub actually goes into a bit more detail about how we arrived at this design where we have this trait. And so all kind of the point being here is that for this code to compile, we actually have to import the trait. If you're a downstream user of PyO3, then the goal is for you to not really have to care that these traits exist when you're changing API. And so in the PyO3 prelude, which basically we kind of recommend that you, at the top of all of your files where you're writing PyO3 code, have this import from the prelude. And in the prelude, this isn't resolving just because we put PyO3 there, then we actually include all of those methods for all of the new bound pointer types. So PyModule methods you can see is here. So you don't really, as a PyO3 user, have to interact with those traits other than you see them in documentation a little bit. They're always brought in for you by the prelude. But for our own tests, we just had to update those. And then what have we got here? This is code that's taking now the wrong type here. Oh, yeah. Okay. And then this is a piece of the Py3 API that's returning a Py module again, py.import to import a module. Unsurprisingly, currently works with the old API. I want to add this function import bound, I guess it will be, which will take which will return in this form instead, but I just haven't got around to introducing that. That's not the right implementation. And it would have the generic argument. Copilot's not done a good job of expanding that. But the idea is that we will have, by the time PyO3 0.21 releases, a new version of this method. Eventually, I'd like to rename import or have import change type directly. But for PyO3 0.21, I want to avoid breaking people. So we're going to add new methods for the new API. And then we'll work to tidy that up over the longer term release cycles. Oh, thanks for joining, Peter. See you around. Okay, so that's. But for now, we're going to have to live with the fact that import only loads the old API. So the main way to get from the old API to the new API is by this helper toBorrowed. Rather than accepting a built-in Rust type, is it possible to accept a custom type? David, oh sorry. I see you've retracted that. Okay, so hang on, other way around. So unwrap first, because this might fail. The import could fail if the module doesn't exist. Built-ins we're pretty sure will exist, so we're unwrapping it. toBorrowed gives us it gets us into the new API. Oh, sorry, not toBorrowed, as borrowed. We need to import that type. Again, that'll be part of the prelude. And then we wanted a reference. And that's now going to compile for the new API. So we've changed the module initializer. As a recap, it was taking a reference to PyModule, and it's now taking a bound PyModule instead. And so I think the result of changing that is that probably we'll find that this code no longer compiles, but the new code does. It gets further. We we might end up, we're going to have to think about wrap PyFunction in a second as well. Any opinion from chat? We've got two problems here. So one problem that we've created is that the old API we no longer support because we changed the type that module initializer works on. And we're going to have to fix this before we go. Or we can go into the new API and we have to deal with the wrap PyFunction, the macro that it was currently expecting to work on the old API as well. So we're going to have to figure out both of these somehow. Anyone got any preference? I think I might keep going on this one here, on solving the existing API a bit first, because this is sort of another context switch. If anyone really wants to see us look at wrap PyFunction right away, we could go there. Otherwise, I think I'll carry on and fix this compile for the older code first. All right, let's go back and look at what we changed. So in our expanded code, we create this initializer, we pass it this function, and we've changed we changed what the initializer wants to be so that the second argument needs to be this bound type. But that's no good because we want to support both. So I think that this is where the proc macro is going to have to change. It's not good enough here for this code to just receive a single function symbol, because that single function symbol doesn't support the two different types that we want. So I think that what we can do is we can go to the proc macro code and modify this to maybe do something like this, where we can always define the types that we want. So this will be, I'm just sort of drafting code inside our expanded procedural macro code here, just so that we can get a sense of what I think we're aiming for. And then we can go and implement that in the procedural macro. So we then call this, and here, I guess we've got this bound Py module, and we know already, because we've supported it in our we added this compatibility, right? We have a way to get from a reference to a bound Py module to all of these three types by going through this bound module wrapper. So I think we want the code over here. Was it like this? Yeah, it's a public field inside. So that's the way that we construct it. And I guess that we want to use a conversion to achieve it. So this could be written this way around, where we're using the into trait to go straight into the type we want. Into is implied by from. So in these traits, we've implemented from, but implementing from also means that into is available. But for hygiene reasons, so inside the procedural macro, we are reliant on the symbols that are imported into this Rust source file. We can't actually guarantee that the Rust standard library is imported. So then we have to basically refer to it this way instead. And that's guaranteed to compile regardless of whether the surrounding source code has imported the into trait or not. So I think we're aiming for that. And so let's go try, and then we're going to have to pass this thing into the module initializer instead. And so let's go find the place in the procedural macro code where we do this. So we're probably looking for, this looks like something we can search for. Yeah, here we are. That looks very familiar to us from what we've just been looking at, with the difference being that we've got some variables instead. Rather than accepting a built-in type, is it possible to accept custom type in Rust functions? Okay, David, just in response to your question, I think what you're asking, let's try and talk about that very quickly, is you want to have something like this, right? You want struct pt Yeah, I think you're looking for something like this. So you want X with, well, maybe I64 or floats or something. And then you want something like this, perhaps, is what you're looking for. So PyO3 already supports exactly this. Basically, if you turn it into a Python class, then on the Python side, you can then have this PT type. Let's just switch back to the terminal. So we're going to need to add the, it's going to be a little inconvenient to compile right now. I think if you look at the PyO3 user guide on pyo3.rs, you'll find a bit more information about these PyClass types. But basically, then this PT becomes a real Python class that you could build from the Python side, and then you could pass that directly into functions. I think that's what you're looking for, something like this. Anyway, let's just comment that out for now. Oops, we overwrote our empty class. Yeah, so that should be compiling again, barring the changes we're making to the macro at the moment. So we were in here. Oh, thanks very much, David. Glad you're enjoying the stream. So we wrote this, didn't we? We wrote this draft here. So let's just put that right there. And what we've got in this procedural macro is, instead of where we can see that we've got real code, we've got these placeholders prefixed by the hash. So we just need to work out the function name we moved to here, and this we want to now pass init wrapper. And I think that might work out being good enough. So what we've done is we've changed the type of the module initializer to want to take the bound type as the new API wants, and then we've added this compatibility wrapper. So let's just document this. So this compatibility wrapper is allowing us to get the result we want, where it takes any of those three types now. I mean, we didn't really need to support the PySmart pointer here, I think, but we do, just by virtue of having done leaning off the solution that we did for the pass module function. So I think with that in place, let's go back here. It looks like this code is now going to compile again. So great. Oh, not quite. That's because I've got this lifetime here, which I didn't express. Let's try again. Oh, and then the problem is also that we haven't, this is exactly the point I was trying to make here. We didn't import bound module, so that it's failing to compile it. So let's, where do we put this? This is in PyO3 impl PyMethods module. Maybe I'll add some new lines here just to make that a bit more readable. Like that. Great. And so now it compiles. Great. So we've got the old submodule type working, and I think we should be able, if we uncomment this one, it's not going to compile anymore because we need to look at wrap_py function. So maybe we'll look there in a second. I guess before that, let's just confirm that things are still working as we expect. So this is now going through all our new code, and it's still working just as it was before, where it's printing the representation of that Py module using the new bound smart pointer. So far so good. We're beginning to hook things up to work for the new API. the last step, I spoke about the documentation coming through. So we just compiled with that. So actually, if we look at or if we look at the help for, I think it's just going to go on the submodule because of the way we set it up. Then we should see, oh yeah, this is the doc for the module. So that little bit has come through from the Rust code. Bit of a side point, but just showing that you can get the Rust documentation to come straight through into the Python. Obviously, we didn't put anything particularly interesting there, but it can work. Great. So the last piece to, I guess, our proc macro puzzles that we've been looking at over this couple of streams then is about getting this wrap PyFunction macro to connect up. So let's maybe re-expand this source code, tidy up a little bit. Let's take the Py class out for now. Tidy that up a bit. So we're looking at this, and then that makes it a bit easier for us to work out what's going on in this wrap PyFunction macro. So let's expand one more time and see what we've got. I'm actually going to close everything else. So here we are. Oh, that's interesting. So changing the procedural macro in the way we did has for some reason upset how the code's coming out. I don't know which bit particularly has done it, but it no longer looks very tidy. But somewhere in yeah, we can see that this is beginning to take shape of looking like what we wrote in our code here with this init wrapper. It's all formatted horribly. I'm not quite sure what's caused that. I think cargo expand, I've seen it do this kind of thing before. I'm not sure whether that's cargo expand that's responsible for that or somewhere else in the Rust compiler machinery. It's a bit harder to read. That's a little unfortunate. But the point being that we were looking for what's going on with this wrap PyFunction and why is it creating a compile error now that we've got the M that we're passing in is the bound PyModule instead now. And so that is that is expanded. We had PyO3 Scratch 2 looking like this, and we've now got PyO3 Scratch 2 looking like this, where the add function call has turned into this wrap PyFunction that we had inside is now this bit, right? And we can actually see that if we click through on the definition of wrap PyFunction, it's not actually a procedural macro, this one. It's what we call a rules by example macro. And so here we've got, we can either pass it one argument or two arguments. The first one being the function that we want to wrap, and then the second one being, if we pass it, it's that module, so that we can associate the right module with the function. We basically always want the two argument form. I think at this point, I might just also gently mention that the future PyO3, I would really love it to look like this instead, where you can write a Rust module instead, and then have this kind of look instead. So instead of needing to do this imperative code to build up the Python module, just write something declarative which looks like a normal Rust module and have PyO3 figure out what it needs to pull into the module automatically. I think would be a nice tidy up. But for the moment, we have this wrap PyFunction macro, and we're going to live with it. Changing PyO3 to work like this would be a backwards incompatible change. So, it would happen by first introducing this new API and gradually changing people's usage of it over many versions. So for the moment, we're going to need to focus on getting wrap PyFunction to work. So inside it, let's focus on the two argument form. And I think In fact, the one argument form doesn't really do much. I think it just allows you to, we can see that it's expanding into a closure again. So I think that all that's going to do is allow you to write something like this. I can't remember why that was useful. There's probably some history behind it. But anyway, so we've got two argument form. That's what we document. And in either case, it goes into this PyO3 internal symbol wrap PyFunction and then forwards on that second argument. Okay. So we want this to work for any of so either the old API or the new API. I think that we have a function in common between them, which is this as borrowed helper. No, that's not going to work if it's this, because PyO module, I think you're allowed to pass in this second one. Where are we? We're allowed to pass Py here, and that was a valid compile. So when we actually have three types we're going to allow Py as a Python, or M as a bound Py module, or M as a Jill reference to a Py module. So there's quite a few different choices there. But that's cool to see, because actually that means that wrap PyFunction is already doing something smart to allow either of those two types. So let's go into that actually then. Here we are. So it's allowed PyO module, which again we're using the into trait. This is good news. We've actually got it in this crate derive utils. Okay, which is another submodule which really should have lived inside of this submodule. I think I'm going to be a little bit mercenary with a refactoring here. It looks like this is the only thing left in derive utils. Is there a reason why this needs to be here? It is actually used in the public API of PyO3. So we're going to leave that. But I think what we probably want to have this for now. But that's still a breaking change. So either way, we're going to end up having to introduce a breaking change to this PyFunction arguments type. I guess if that's it, then let's just live with it like that. Might as well express the two lifetimes correctly. Good. Thanks for joining the stream, Norman. Nice to see you here. So we're going to have to try and adjust this PyFunction arguments type for the new API is what I'm thinking. And then we'll work out how we get all of the types to be what we want. Please excuse me. I've been suffering a little cold this last week, so just going to need to clear my nose. Right. Sorry about that, everybody. So by changing the type, we've added a new lifetime. We want to change this function to also deal with the new PyO3 API, I think. Yeah, so we're going to need to express both lifetimes here. I have to tidy these up to also deal with these new lifetimes. I like in code, in the old PyO3 API, there was a lot of mixture between whether just using A or Pi for the name of the lifetime that appeared once. Because in the new API, we kind of get a bit more expressibility on like the lifetime of the reference versus the Pi lifetime for the global interpreter lock. I prefer to be a bit more consistent and be like A is always the lifetime of the reference and Pi is the lifetime that we're interacting with the global interpreter lock, just for clarity's sake. So we'll have a go with updating all of these now. So in the old API, because those two lifetimes were tangled together, I think it looks like this. So we're not actually going to be able to use a reference to a bound here because this old API isn't going to be able to give us a reference to one. So I think in the new API, we actually have one other tool at our disposal, which is this borrowed type. The difference between that and bound is that bound contains the pointer and owns it, and borrowed contains the pointer but is borrowing it from somewhere else. And so it takes two lifetimes. So we've got a reference to bound is a pointer, because a reference is a pointer to another pointer, whereas borrowed instead has two lifetimes, but it just is a pointer. And we're needing this here because if we tried to compile this way around, I'll show you what breaks first. So to go from this old API to the new API, the function we want to use is as borrowed, and that gives us a borrowed. This trait is in the prelude, so you don't need to worry about that. And we need a reference, is what we stipulated here. But the problem... Oh, why is that not? Oh, we've imported it already. I'm expecting that this will fail to compile in a bit. I think we've got some compile errors somewhere else that we're having to fix first. Oh yeah, because we put two lifetimes on it. I guess we'll just do this for the moment and see where we get. Interestingly, this is also a GIL reference. It's to a Python function object. So wrap PyFunction is creating a Python function. It's also using the old API. So we probably need to update this, but we'll worry about that in just a second. Maybe I'll add a to-do there. And if we have time, we'll look at that. I think we're probably not going to have time to do that this week. Whether I do that off stream or we end up doing that in a future week, I don't know. And what other compile errors have we got? Let's try find it. We're getting types function. Yeah, so the problem with breaking this is that we're going to end up creating a breaking change to the PyO3 API. I sort of wanted to not break the existing PyO3 API introduced, or at least as on the user level code. And the problem is that this PyFunction arguments type is user facing. I think we probably do need this to work like this. Probably the constraint is that we just can't add a second lifetime. So maybe if we just do this, No, that's not going to work very well either. We are going to need to have 2 lifetimes. I think let's proceed forwards and get the compile to work. And then we might have to come back to this and work out how to not break the PyO3 API by adding 2 lifetimes to this type. Probably we're going to need to separate the type out and end out with one type, which is public, which we can not break, and then one type which we'll use inside of PyO3's internal code, which we can freely break as much as we like. And that might be the better approach. We're ending up in a bit of a lifetime tangle. Where is this coming from and why? It's because that moment when you know that Rust lifetimes are really biting you. Lifetime parameter essentially is lifetime pi, but lifetime parameter must live lifetime a defined here. Yes. This is because of what we've expressed here, actually, I think. So because we put a reference in, I was expecting us to get the compile error down here, but actually the compiler's hitting it even sooner. And I think what's going on is that this reference we've expressed with lifetime A, which is what we're seeing here, the lifetime parameter must outlive the lifetime A. That's because this type has lifetime pi inside it. And for this reference to live for lifetime A, then this type has to be alive for all of that lifetime A. So that is itself placing a hidden constraint that pi has to be longer than A, or at least as long as. That's fiddly. And so that's actually another reason why we might want to turn it around to be like this, because the borrowed, it's not a reference in the same way. These 2 lifetimes can actually overlap in different ways. And so other than that, this borrowed works very similarly to bound. You can actually go from borrowed to bound. That was what we were doing down here. But it's just holding the pointer with slightly different constraints. Yeah. I think just for the sake of not break, well, let's break it for now. And then if we need to think about backwards compatibility, we could talk about that just at the end. I think I've got about half hour left on the stream today, by the way, folks. I'll probably wrap it up there because, as I said, I'm suffering a little cold. I've been going for about an hour and a half at this point. We've been doing 2-hour streams, and I think that's quite a good length, and particularly today with the cold, I don't think I'll manage to make it much past 12 o'clock. Okay, so we just need to tidy up how these are working. We might need to think again about how this works. This, anyway, we can now have written like that. This one's a bit more interesting. I think it might want us to just generalize that. Okay, so that's better. Are we now compiling? Oh, and then we've just got some other definitions where we need to change these. to use the Pi lifetime now. Yeah, there's a... and then we've got one final step to do, according to what we see from the terminal, which is that we need to get that final from implementation working. Which is this one for our reference to our bound type. And this one we can express both the lifetimes in the way that we've been expressing everywhere else. And we don't need to do anything to convert it. Oh, yes, we do. And I think that this should now hold out. Okay. It's all getting rather sticky. So what we're getting in the terminal error on the left is that now that we've solved this bit with changing this PyFunction arguments type, we've ended up going one step further and finding that sorry, it's in here. So the add function in the new API, it takes a bound reference. In the old API, it takes a reference to an older a dual reference instead to the Python function. I think we're going to get a bit stuck here because I can't think of a good way to get around this. The problem is if we go back to this code that we've fixed how wrap PyFunction is taking m in, but wrap PyFunction, we've now changed it to return the wrong thing out. Oh no, we haven't changed what wrap function produces out yet. Maybe we can still get there. We might have to go further though. And make this more generic, perhaps. Because I can't see any other way that we can avoid. So one option is that we could just go for what the approach we've been doing in a lot of the other places with regards to the PyO3 API is, and introducing a new variant of wrap PyFunction. That might end up being the nicer idea here, because having gone a bit down the rabbit hole, what we've found is that changing that wrap PyFunction macro to accept the new type has introduced quite a few changes across the code that I don't really want us to have. So let's go backwards, actually. We've only changed this file for this. So let's go backwards and throw away the changes we made to this file and also that file. And now we should be in a place where, oh no. Now we should be in a place where we're back to, oh no, there was one other place where it's not working. This is proof that it's not scripted, right? We've run into a bit of a dead end there, so I'm having to back out. We're trying to figure this out as we go. Yeah, so now I think we're back where we went to before. And so, for want of a better idea, I think we're just going to introduce for the moment, maybe we can come up with something smarter later, just a duplicate of all of this, which works on the bound variant of this instead. And then we can just copy all this. It's a bit unfortunate to do this duplication. But I think it's going to create fewer headaches. So now we can have this type take. Oh, I should have really copied all this before I thought about doing that. Never mind. We're going to have to type this out again. Shouldn't be too hard to fix this up because we've done it once before. We'll see what we get if we carry down this line now. I think we should be able to get something that compiles. What we've got to do is just add this pi lifetime in because we put 2 lifetimes in the original, in this new definition. It's worth pointing out that if you're a PyO3 user, then in general, I don't think that this sort of stuff is going to cause you the same degree of complexity, because you can probably just move over to the new PyO3 API without needing to worry about your Rust code trying to be compatible with all of the existing code which people might have written out there. So it's kind of like we're trying quite hard for PyO3 0.21 to not introduce a whole slew of compiler errors from introducing this new API. So as annoying as it is to have to copy paste and duplicate some of these things, I think it does lead to a better result for users when they're updating. So what have we got now? We need to introduce this type as well. For now, I'm going to leave that. Oh no, we need this to be. I think we need this because that's exactly what we were finding with the new API, that we need to get the result to be a bound smart pointer. And I guess we're going to have to figure out. Let's just duplicate this again. I think we can probably tidy it up. But once we've got something which compiles, then I think we can learn quite a lot from that and think about how we can reduce this back down. So we are nearly there, I think. Oh yeah, we've got the same lifetime error that we saw before. But this time, rather than changing the way that we're defining the enum, I think I am just going to say that that we have this constraint here. And where do we end up now? We end up, hopefully, we might have some problems with tests, but we're getting closer. yeah, the error we've got is now back in this function that we duplicated here. So internal new, what's going on here to try and explain a little bit. This is deep in the PyO3 machinery where we're creating, oh, this probably doesn't need to be public anymore because we're calling it from inside PyO3's machinery now. So it's the function which takes, given a Python method definition. So we talked about those a little bit last week when we were looking at the C API. It's basically the definition of what the Python function should eventually look like. So it contains the function pointer, the name, the documentation. We actually go and then call the C API. Where do we go? Oh yeah, down here, PyC function new EX, to create one of these Python function objects. So it's literally creating the thing that then you can handle in the interpreter and call and do all the normal Python operations that you might expect from a Python function. And so I think that the only change we need to make here is we need to change the way we do that. So this is building the old API, an owned pointer. It's checking for errors. So in the new API, we've got a different helper that we can use. And we're not checking for types because we're assuming that the Python interpreter, when we call PyC function new EX, is giving us a Python function object. So we can do that. Oh yeah, and we just need to carry ownership with us. We don't need to take the result off. There we go. So that's the right invocation. So we've actually not changed a huge amount. Consider following the following lifetime by A outlives pi. Why have we got that? Let's think about this for a moment. That's a bit of a surprise to me. So let's see if we can get the compiler to highlight. It's returning data with lifetime A. So for some reason, maybe let's check here. Oh yeah, we're using the wrong lifetime here. That's more likely to compile now, I would hope. And we've moved the problem somewhere else. Oh yeah, this needs to be updated as well. Are we there? I think we're going to be following these lifetimes a little bit further through. Oh no, we're back to the original error. So now that we've changed the machinery in the middle, we haven't yet changed that wrap_py function macro. So as a final step, let's go back to that wrap_py function. And so I didn't really want to have to do this, but if it's the only way that we can get things to work for now, then I guess that's what we're doing. And we'll at least be able to clean this all up in a future PyO3 version. So for the moment, it's going to create a little bit of a mess, but we'll get there in the end. And then the last step is we're going to need to add this to the PyO3 prelude in the same way. Oh, this all gets a bit more new stuff than I wanted to have, but I think we might be there. Yeah, okay. And then the final detail is that this add function was taking a reference to a bound, but wrap_py function bound is creating new function objects, and so it's transferring the ownership of them. If we go back to the definition, it's not got a reference to them. It's actually fully owning these things. We talked about the ownership on these bound smart pointers before, and how this is owning a Python object here with the bound. If we were to carry as a reference, we're just borrowing it. But because we're creating new, we have to hand out that ownership to somewhere else. So that has to stay like that. And so we're going to have to introduce a reference in there. And finally, we're at a point where it's actually working, right? So if we now compile again, I think we finally see Oh yeah, we called this thing 2, but we don't want that. That's what the final warning we've got is. And we gave our Python module the wrong name. Great. So finally, I think we've got there in just about the 2 hours that we wanted. So this is the Python function object, which wrap_PyFunction bound has been creating. And if we call it, we're still getting that same result we got back at the beginning of the stream, where all it is it's taking the module that it's defined within and printing the wrapper of that module. So it doesn't look like we've achieved very much from a new functionality perspective. It's not going to break any ground, but I think both of these changes were pretty fiddly procedural macro changes. And they're necessary if we want to get people away from these old APIs using reference to PyModule directly, then we kind of need to make that migration story as clean as possible. And so for the pass module case on PyFunction, which we solved today, it's nice. We can just change the type and everything continues to work. For PyModule, it looks like, well, I might go have a little bit more of a think about this off stream, but we've just got 2 things with the same name. We'll just fix that. It looks like, as well as changing the type, we've had to go with a little bit of adjustment here. Instead of just calling wrap_PyFunction as you did before, we have wrap_PyFunction bound and introduce a reference. I think I can get one bit further, actually. We could change wrap_PyFunction bound to... oh no, maybe not. Because it's inside a block, I don't think it'll work. I was hoping that we might be able to get wrap_PyFunction bound to emit the reference as a sort of temporary expression. I guess that might work like this. But I think for this case, the 1 argument case, it just doesn't work because the closure producing more complexity. Let's have a play. If we do that, does it work? Now we can definitely take the 2 argument form and no, it doesn't quite work because we've got the references here. Oh, but that's fine because we could do as. That's not going to quite work. I don't think this is going to work out. I was hopeful that we could avoid that, but I don't think that will. Okay, so that's where we got to, and we need to add the references back here. So yeah, for the new API migrating your PyModule, you're going to need to change the type that you get in, and you're going to have to swap the macro to a new _bound form. And so there's a few different places in the new API where you're going to have to like opt in a little bit. It's a little bit annoying to have to introduce another one here, but it's not the end of the world. So cool. I think that is a pretty nice place to wrap up for today's stream. So let's commit that code. Let's just give this a commit. Name that's sort of fine. And then what am I going to have to do to tidy this up off stream? So I guess the follow-up, I really might try and do the rest of this wrap up off stream rather than subject you all to a 3rd week in a row of this same problem, because I think that the remainder is less exciting from an implementation perspective. We'll have, oops. I wanted to go to the PyO3 user guide. Then let's make that a bit bigger. Then all over the documentation, we've got examples where we show the old API, right? And I think I'm going to have to comb through these docs and update them to show the new code, which is easy enough. That's a fairly mechanical change that I can just work through. And then we've also got this migration guide that we're putting together. We're on the current released one. So if we go to the main version, I've started putting together notes on how to migrate from PyO3 0.20 to PyO3 0.21. And because we're talking about this new bound smart pointer, there's quite a lot of detail here, trying to make this as smooth as possible. And I've got a section, I mean, we made a few other changes in 0.21, which in hindsight are a little bit unlucky, but it's all sort of come to a head where we felt like we needed to do it in one go. And so I was talking about how to migrate from the GILREFs API, or the old API as I'm calling it, to the new bound smart pointer. And I guess I'm going to have to add some detail here, maybe even a subsection about this transforming PyModule, because it's going to be a little bit detailed, but at least it will compile in the new code. And it's the sort of transformation where a user won't have to think too hard in review to see, oh yeah, they swapped the type, they added bound to the name, and it should be fairly reviewable for everyone downstream. So it's a little bit unfortunate that there's been some churn here. It would have been nice if we could just have these bits work and all they needed to do was swap the type, but I think for the sake of being able to move forward in a practical way without breaking existing code, that looks like it makes sense to me. Cool. Thanks very much for joining the stream, David. Anyone else got any last minute questions? Oh, sorry for the sniffing on stream, everybody. It's, the cold has been not fun this week. I also said that we might take a look at the what we've got remaining. GWS. I'll get well soon. Thanks very much, Amarud. And hopefully when I think I'm expecting to stream next week at the same time again on Friday morning. And hopefully I will have a clearer nose and be able to speak just a little bit easier again. Thanks very much. I did mention that we might take a look at what's remaining to get this new API out the door. And so I have an issue on the PyO3 issue tracker with a whole load of bullets on it, talking about at least what I'd noticed as the things that needed to be done to make it kind of releasable. I think internally PyO3 is still probably going to have some tidy up to do. I think it's more important in my eyes if all the user-facing code has at least the option of migrating away. Probably there will be a few edges that we don't catch, but in general, we've got all of these new methods for all of the bound smart pointers working, barring on the type objects. And I think that one was waiting for us to finish off these changes that we've been doing today. In particular, things like class method was all related to how these type methods were working. And so I think that one, hopefully we can get merged soon. There's things like the derive from PyObject prop macro. I don't really want to talk about that on stream, but there's documentation on the PyO3 user guide about that. Internally, I think user-facing code doesn't need to even know that we might not get this changed to PyO3 0.21. We could probably do it in a patch fix and nobody would notice, because all it would do would be changing what gets generated by the procedural macro. I don't think there'd be any user-facing changes there if we did that. There are certainly some bits down here which haven't been finished yet, but once these items are kind of done, then maybe I'm hoping that this can happen by the end of February, really, or sooner. And so if you're interested in joining in, either by providing some implementations for pieces of these issues, or just reviewing the code that I've already pushed. I've also been tracking reviews that we've got remaining at the top, and people are getting to these when people are available. It's very much a volunteer project for the bulk of PyO3's development, so it's helpful for anyone who's interested to really come along, and there's a scope for people to get involved. So maybe we can get this shipped before too long. And yeah, I think that's about it. Thank you very much, everybody, for joining the stream this morning. I guess I'll figure out what we'll be tackling next week. I might try and do something a bit different to the new API, but at the same time, if we're focusing on getting this new API complete, then it's kind of the main thing that's filling my mind space at the moment. So we'll see where we go. But either way, have a great weekend, everybody, and I'll see you all next week.